Now, we want to basically move the covariant derivative from here to the field by means of a partial integration, and that gives the torsion, and the torsion will turn out to be 0 by means of this field equation. So how do we do that? First, well, we freely raise and lower indices because we remember that del eta AB is equal to 0. And the second thing is that we can show that similarly, actually it follows from that, the epsilon tensor is covariantly constant as well. So with any kind of indices, raised or lowered, the epsilon tensor is covariantly constant. How do we prove it? How do we prove that? Well, we work out the covariant derivative of the tensor, and that is equal to the exterior derivative plus omega. There is an omega for every index. They are all upper indices, so you just have to sum for similar contributions. Now, this is 0 because epsilon is a constant, and the rest is 0 because you can check it for every choice of indices. So, for example, A, B, C, D equal 0, 1, 2, 3. If you do that, let's replace 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Now you know that the epsilon tensor can only be non-zero if all indices are different, so this must be 0, which means that this is 0. This must be 1, which means that this is 1. This must be 2, which means that this is 2. And this must be 3, which means that this is 3. But by the metric compatibility, omega 0, 0 is 0, omega 0, 1, 1 is 0 because it is antisymmetric. It is antisymmetric after you raise the indices, but the eta AB is diagonal, so omega 0, 0 is 0 no matter what kind of indices it has. This is actually not sufficient because we should also check that when two indices are equal, let's say A, B, C, D is equal to 0, 0, 1, 2, that is 0, of course, but what about the right-hand side? Is it 0 or is it something else? Because if the covariant derivative of 0 is non-zero, the identity is wrong. So let's try with two equal indices, A, B, C, D, 0, 0, 1, 2. So that is 0, 0, 1, 2, 0, 0, 1, 2, 0, 0, 1, 2, 0, 0, 1, 2. Now here we have epsilon with two equal indices, so that is 0, of course. But here we have epsilon with potentially different indices. So here you have 0, 1, 2, which means that this must be a 3. And here you have 0, 1, 2, which means that this must be a 3. And the omegas are omega 03 and omega 03. But you see that they are multiplied by epsilon 3012 and epsilon 0312, and since epsilon is antisymmetric, the result is still 0, and so on. So you can convince yourself that this is correct. And now we can use that to write the variation of the Palatini action as a total derivative, the integral of a total derivative plus something. So let's write it as the del of everything and when you compute del of everything, you will have del of this, del of that, del of that, del of epsilon, which is 0. So del of the first thing is what you have here. And what you just need to subtract is what you get when you compute del here and here. By the way, both give the same contribution twice because they are one forms. This is a derivative. And so taking that into account, let me claim that we get this. Factor 2 del EC ED epsilon ABCD with this sign. So del here and del there give the same contribution because when you cross a one form you have a minus sign, and then when you so if we write this, that is equal to del AC ECD minus EC del ED. But that is also equal to del EC ED minus del ED EC. Why minus? Because now this is a two form. So the covariant derivative of a one form, so it's a two form, so it commutes with a one form. And so when you exchange both, you do not change the sign. And then to change, to turn this into that one, you need to exchange C and D, but due to the anti-symmetry, you take care of that sign, and so you get twice that thing. So the twice is okay, but what I want to show you that in this partial integration there is no minus here, but there is a plus. And again, the reason is that when you compute this covariant derivative, you have the derivative of everything, and when you move the derivative on EC, you have to cross a one form, so you have minus this. So you correctly subtract that. Okay? So when you cross this one form, you get a minus, and so at the end, when you compute that covariant derivative, you just remain with the unique term that we had. Now, this is a covariant derivative, you see, of a form. It's a four form that has no flat space index. Well, it has four flat space indices, but they are all contracted. So that is equal to the exterior derivative. It's the covariant derivative of scalar. Everything is contracted. From the point of view of flat space indices, nothing remains. And so we have the integral of a total derivative, which by the Stokes theorem, remember, the integral on m of d of something is equal to the integral on the boundary of m of that something. But on the boundary, by definition, the variation of your field must vanish even if there is a boundary, so we do not care if there is or there isn't. On the boundary of the manifold, the variation of your field must vanish by the variation of calculus. That's how it works. And so that contribution goes away. And we remain with the other one, which isolates the torsion. And we want to show that this being 0 for every delta omega AB implies that the torsion is indeed 0. Now this is just an exercise with indices. Just have to do it and to check that this is indeed correct. So again, we have written that as 1 over 2k squared delta omega AB. Then we have the torsion, let's call it TC ED epsilon ABCD. Well, so now we have to introduce space-time indices to see what's going on. Omega is 1, the torsion is a 2 form, the field line is a 1 form, so you get epsilon mu nu rho sigma d for x. Well, you would get dx mu, dx nu, dx rho, dx sigma, but we know that dx mu, dx nu, dx rho, dx sigma is epsilon mu nu rho sigma d for x. Here it is. And epsilon ABCD. Now we can drop those things. So this is 0 for every delta omega mu AB. And as long as this coefficient is antisymmetric in A and B, which is true already, so you don't need to antisymmetrize, we can conclude that 0 is equal to T C nu rho ED sigma epsilon mu nu rho sigma epsilon A, B, C, and D. Or if we want, we can now convert everything to the same type of indices. If we want, we use everywhere flat space indices. And then here we will have Mn. We have some index instead of mu, so we multiply by E mu F, let's say, which means that this index goes into F. Nu and rho we will convert, they are contracted to M and N, and the index sigma is already converted into D by the field bind, so we don't need to convert it once again. So that index is D. And we want to show that this implies that all coefficients Tc Mn are 0. We have two epsilon tensors which are contracted by means of D, so we know how to compute them. The contraction, that is a certain determinant with minus, because we're in Minkowski, a determinant of delta functions. And the three indices are Fmn, ABC. Fmn, ABC, ABC, ABC. So how to compute this? You can compute it from the first row, for example. So here we have delta Fa, and then delta Mb, delta Nc, minus delta Nb, delta Mc. This gives a factor 2 because this is anti-symmetric in M and N, and that's why I calculated by columns, because I always, all three terms here, I will have anti-symmetrization in M and N. Delta Bf plus delta Fb T something, Tc, yes. Delta Bf gives delta Am, delta Nc, minus the same thing. And the last contribution is minus delta Fc, which means Tf, delta Am, delta Bn, AB, times 2. We get this identity. And then if we choose B equal F, we have 0 equals to minus 2 T B C C, T A B is equal to F to T A C C, T C A C, plus 2 delta BF becomes times 2 times 4 TACC. The last one is minus 2, B is equal to F, so it's again TAC. So you have 8 minus 4, 4 TACC, which means that TACC is 0, but if TACC is 0, this is 0, this is 0, so TFAB is 0. So you have to get familiar with these kind of operations because we will meet them all the time, and because once you understand how to move in these kind of things, it will become very natural. Now, so the first field equation, the equation of omega, gives vanishing torsion. Now we have to work out the equation obtained by varying with respect to E. That's easier, actually. Could have done it first. So delta S Palatini it means that we have to vary this. So RAB doesn't change because it depends only on the spin connection. Then we would have delta EC ED epsilon ABCD plus the same thing with EC delta ED. But again, those two give the same contribution because now this is a one form, this is a one form. When you exchange them, you get a minus. And then when you exchange C with D, you get another minus. So you get 2. So we want that to be 0. And check what happens when that is the case. So delta EC is a one form. So let's write it as AC M EM. We can expand it into the basis of one forms. So that means that this must be 0 for every matrix ACM, which is a generic real 4×4 matrix because it has no symmetry properties. It's the most general variation. So 0 is equal to delta Palatini, which is 1/2 k squared integral on M of what? Let's write here AB Mn EM En divided by 2. Let's write delta EC as AC P EP. And then we copy ED epsilon AB CD. Now again we use an identity. This is the product of 4 one forms, and we know that it is equal to the epsilon tensor times E times D for X. So we get 1 divided by 4k squared integral on M RABMN ACP. Then we have E d4x times the epsilon tensor with indices M, N, P, and D. and then we have epsilon A, B, C, and D. And again, we have two epsilons with one contracted index, and we can, well, first of all, we can already write what this implies, that 0 is equal to, well, actually, let's keep it that way because later we will need also the coefficient in front of it. So let's not skip, let's not drop that already. So 1 over 4k squared integral and these epsilons give again a determinant of products of delta functions. And the indices are M and P and ABC. So now it is convenient to calculate it along this row so that M and N are always giving, since this is anti-symmetric in M and N, they are always giving two contributions, two equal contributions. So the sign is plus, we get minus 1 over 4k squared E d for x times what? First contribution, delta PA, that means A CP, PA, MB, these two are equal, and C. When these two are equal, you get minus the Ricci tensor, because that's the second index and the third one. So you get minus the Ricci tensor RAN, but n is equal to C. Careful, this is not the two-form RAB now, these are just components, so this is the Ricci tensor, although it might be confusing to write it by means of flat space indices, but be careful here. And there is a factor 2 because there is delta Mn, delta Bm, delta Nc minus the other one, so a factor 2. So we have computed this one, now we compute that one. Delta Pb with a minus 1. So there's a minus. Delta Pb, so ACB. And delta Ma, delta Nc. Delta Ma means that this is a Ricci tensor RBC with plus. And there is a factor 2. So here there is an n was equal to C, that is a C. Last term, delta PC. Delta PC means that here you have a trace plus A, C, C. Then delta PC multiplies delta MA, delta NB, delta MA, delta NB, that is the Ricci scalar, and it will be again multiplied by 2. So there is a factor 2 in front of everything. And we can collect also a minus, so we write 1 divided by 2k squared integral of m ed for x a two indices, whatever they are. And then we see that here, well, let's collect a factor of 4. Because here we have two equal contributions. See, from this and this are equal. ACP, the first one was delta PA, so ACP means ACA. These are two equal contributions, so here you have just RAB. Then we have collected a minus 4 minus 1/2 delta AB R. So when this is 0, for every A means R AB minus 1/2 delta ABR equals 0. And if you want, you can go back to flat space indices, raise or lower the indices or convert them into the metric. And again, let me remind you that this R is rich. So can play around with these conversions of indices, but in the end, what you obtain is obvious, and that's precisely we have not used any metric, any torsionless condition here, although the second equation, the other equation which we found, told us that the torsion is 0. So the combination of the two equations, torsion equals 0, and this is equivalent to the equations you are familiar with. Okay, so this is the first order formalism. So S Palatini in the first order formalism is a functional of E and omega. But we have seen that the omega equation can be solved. What if we introduce the solution inside? The omega equation can be solved. Torsion equals 0. Because the metric compatibility was already assumed from the start, and when you have both metric compatibility and torsionless condition, then you have the solution, which is the Levi-Civ interconnection with the metric and this thing with feedback. So you can build this action, which is the same action, but now it depends on E in a very complicated way, because E is where it was before, but now E is also inside omega. This action gives the same equations, and this is called the second order formalism. which means that if we vary this action with respect to E and work out the field equation, we have to vary here and here, we get exactly the same field equation. Why? So this is a different action. Let's call it S tilde. Because it's just a functional of E. That's its definition. So what is the variation of this S tilde E with respect to E? Here we do not need to make new calculations because we just apply the definition. And we first vary here and second vary there. So that is the derivative of the Palatini action with respect to E with omega constant plus the derivative of the Palatini action with respect to omega with E constant times the derivative of the spin connection viewed as a function of E with respect to E. However, this is zero, because the variation of the Palatini action with respect to omega with E constant is precisely zero when omega is replaced by the solution of that equation. That was the equation of omega. So that you can also write as, think a moment, but it's like writing it like that. Should be actually written like that, with the E constant and omega replaced by omega of E. So should be actually written by that, like that, to be precise. Because you have to differentiate with respect to omega as if omega were a variable, and then you have to replace again omega with E. But this is precisely, omega of E is precisely the solution that makes that derivative vanish. And so you do not need that. Which means that the field equation of this action is exactly the field equations we have just found once omega, after that, is replaced by omega of E. Let me write it this way again. So that means that if you take the previous field equation, this one, and you insert the solution of the other field equation, the torsionless condition, you get a certain field equation, which is the final one, but you get the same here. That's written in this notation. So the two formalisms give the same equations. We can complete this by considering the cosmological term. So the cosmological term is lambda divided by 24k squared plus the rest. Here we do not have any omega, so that just contributes to the field equation of E, and we do not need any further discussion. The variation of respect to E can act in 4 different places, but by anti-symmetrization it will be the same. So you will have 4 times the same thing. But delta EA was written as some matrix big A times the same forms. Then we use again the same identity. We have 4 field lines, differential forms. So this is E d4x, the epsilon tensor. So that is AM, epsilon tensor MBCD, and the other epsilon tensor ABCD. Now you see that you have 2 epsilon tensors with 3 indices contracted. That is minus 6 times the delta function. Minus 6, so 1 over k squared, integral m e d4x a. We have to add that to this. So you see you have something similar to this, delta AB, AAB, but instead of having minus 1/2, there we have just minus. Let's check. Just have minus. And so in total, we obtain this equation. And here, instead of having minus 1/2, we just have minus, and I forgot lambda, I guess. It's lambda. This is not 1, this is lambda. Instead of r, you have lambda. Or this is the same combination that appears in the action.